Today we're going to take a look at section 2.6, and we're going to encounter our trigonometry functions. These are the basic 6 trigonometry functions that you'll remember, and they're sort of set up in pairs. Your homework or your worksheet that you're looking and filling in sets them up in pairs as well. They're structured a little bit differently across your page if you've printed that handout out, but they're actually grouped together for a reason. As we work through them, I'll show you what I mean by that. So we're going to start with the derivative of the sine function. I know that some of you have actually done this part of calculus before, so I'm going to ask you, and if you don't know, it's okay, but does anybody remember, if you have taken calculus before, what the derivative is for sine? Do you remember, Zach? It is cosine. Very good. And Zach, I'll pick on you. Do you remember what the other one is for the derivative of cosine? Very good. Those tend to be the ones that sort of stick out in our minds. They're pretty nice. And so these two are sort of grouped together because they kind of go back and forth between each other. So it's a very interesting thing, right? If I take the derivative of sine, I get cosine. If I take the derivative of cosine, I get negative sine. And then if I were to take the derivative of negative sine, I'd get negative cosine. And if I take the derivative of negative cosine, I get back to sine. So they just have this sort of a cyclic pattern to them. And they're cyclic functions, so that's kind of cool. But they have this ability to keep taking derivatives indefinitely and keep coming up with a sine or a cosine function, and they just cycle between themselves and their negations. Do you remember anybody from the derivative of tangent? You're very close. It's just secant squared. Yeah. Secant squared of x. That's pretty good to remember even those details. These are the last 4 are the ones that people tend to not remember very well. Do you remember cotangent? No? Okay, it's cosecant squared, but it has a negative in front of it. And the last 2 are the least commonly probably remembered. The derivative of secant is secant tangent. And the derivative of cosecant also has that another negative sign, and it's cosecant cotangent. These are grouped in pairs because they feel very similar, right? The 2 at the top just go back and forth between each other. The 2 in the middle, tangent and cotangent, they're the secant and the cosecant, they're both squared functions of the other pieces. And then secant and cosecant here at the bottom, they're very similar as well. The other thing that you might notice is take a look at cosine, cotangent, and cosecant. What do you notice that they all have? A negative. They all have a negative in them. So all of the ones that start out as a co-function, their derivative is a negative something. That's another interesting feature to keep in mind, a mnemonic to remember, right? Something to remember. So what we're going to do next is we're going to just get started. We're going to take some derivatives of these things. So the first one we're going to do is a pretty basic one. However, I want you to recognize that taking a look at this, there's a chain rule. Now, you may not look at this and see, I don't even see any parentheses, so I don't know what you were talking about. Where are there parentheses, although they're not written in? Before and after what?
I mean, with the forward, like the forward parentheses.
Nope, nope, that's not it, but it's a good guess.
Is this after the sine and after the x?
Okay, very close. So it's right here, actually. So when we write the original function as it was written, the 3x is understood to be the value that's inside of sine. It's the angle for sine is what it actually is. It's the angle measurement. If you were to put sine into your calculator, most of your calculators will automatically put a parenthesis next. Do you guys know what I'm talking about? Well, that's what's here. That's that parenthesis. And the parenthesis automatically closes behind the multiplication factor 3x, unless it were told to you otherwise. The only way, so Brooks, you mentioned maybe it being like that, right? The only way it would have started like that, it would be this, is that actually put the parenthesis there to start with. So it is understood that if you have this right here, this is the interior angle. So that's the chain part of what's going on, okay? So what you've actually got is the inside function is the part that's in red. That's the 3x. The outside function here is the sine part, okay? Now the 4 that you mentioned over there, Zach, is just a constant multiplier. If you'd had a variable there, it'd be a different fact. But since it's just a number, it's just part of the derivative. It's a constant multiplier rule. So we write down the 4. And then we're ready for the outside function, and the outside function is sine. So what's the derivative of sine? Cosine. And it's cosine of the same inside that it previously had, just like when we were doing the chain rule in the last section. The inside never changes, so this angle does not change. But we do have to multiply by the derivative of the inside, which is 3. Now, do not sort of be misled by the way that this is written. This 3 is not times the 3x, right? This 3 is times all of this. It's times the 4 cosine 3x, which means this 3 is going to multiply by the 4 when we simplify it in a moment. Okay? And then we're not done quite because we still have that minus x on the end. So what's the derivative of negative x? Negative 1. Okay. So we did the chain rule part, and then we had this additional minus x part to do after we did the chain rule. So the simplification step that we already mentioned, is simply to write this as 12 cosine of 3x. You can put the parentheses around the 3x or not, and then minus 1. Any questions on that one? It's a pretty basic one to start with, but it's going to get complicated pretty quickly with the next one.
So you'll use a chain rule always for the trig functions unless it's
Unless they just have x in the middle of them, yep, you will. And most of the time, that's not what they have in the middle of them. There is something else in there. So a lot of times when we have trig functions, we have chain rules involved. Very, very good observation. Okay, take a look at this one. Tell me some of the things you're seeing as you look at this. What kind of derivative rules do you see that we're going to need? There's several of them. We're going to need a quotient rule. Yep, what else? Going to need a chain rule. We do have one. Do you know what it is where it's going to be, Zach? Can you tell?
Cosine and
The 2x part inside of there's an inside one, kind of like what you were saying, Tyler. There's actually another chain rule involved in this one. We're going to have 2 chain rules. Does anybody else see anything else? What about the x squared on top? What kind of rule are we going to need on that? Power rule, right? Yeah. You guys almost don't even think of that as being a big deal anymore, do you? Power rule is pretty simple compared to the other ones we've been working with. But yeah, we need the power rule as well. All right, so let's take a look at what we have. One thing that it might be good to remember, and this came up on your exam on a few of your papers, is to remember what that 4 right there means. What we really have here is we really have the cosecant of the 2x, and that is an inside function, like Zach said first. And all of that is raised to the power of 4. Okay, that's what that little 4 after cosecant itself means. It means that the entire denominator is raised to the 4th power. And this is where I mentioned this just a second ago, is that notice I have the inside function that is the cosecant of 2x, because it's raised to the 4th power, right? And then I have an inside function of the 2x, because it's inside of cosecant. There are 2 chain rules involved in this particular derivative, and a quotient rule, and the simple power rule on top. All right, so which is the overarching rule? What's the big rule? Where are we starting on this particular one? Can you tell? Quotient, absolutely. We have a quotient. We have a ratio of one thing down to the next. Okay, there's a ratio between these two. So the overarching rule that we're going to use is the quotient rule. In the middle of using the quotient rule, we'll use the other rules as well. So my quotient rule is what I'm going to start with. The quotient rule says, what do I do first? I write the denominator. So this is the cosecant of 2x raised to the 4th power. That's my denominator. And then what do I do? Derivative of the top, which is 2x. And then a minus sign, right? Okay, now what? Minus the x squared. And we have the worst one for last, the most difficult piece of this for last anyway. All right, so I need the derivative of cosecant of 2x to the 4th. So the first issue is that I have all of this stuff raised to the 4th power. So what do you do when you have something raised to the 4th power? Move the 4 down, we rewrite, and we change our power to a 3. So the first outer rule is about this power of 4. So I'm going to bring my 4 down. I'm going to rewrite the cosecant 2x, and I'm going to raise it to 1 power less, which is a 3. Alrighty. So we did the derivative of the power 4 part. Now we're stuck inside the parentheses where I've got the cosecant part. So now we're talking about cosecant. What's the derivative of cosecant? We just learned this one. Negative cosecant times cotangent. And it's a negative cosecant of 2x times the cotangent of 2x. Because the inside angle doesn't change. The angle started out 2x, the angle's still 2x. This piece is the derivative of the cosecant part of my function. And the last piece is the piece inside in red. And what's the derivative of that piece? 2. And then all of this needs to be written over the denominator squared, right? So I have cosecant of 2x to what power? To the 8th. When I raise this to the denominator right here originally to the power of 2, I've got to multiply the 4 times the 2. That's going to give me 8 of those in the denominator. Okay, so this looks really messy, and it's going to clean up so quickly and so cleanly. You guys are going to be like, whoa, that was kind of cool. So watch with me. What are some things that you notice that we can simplify between, let me say it this way. Let me start back. What are some things that you notice are the same in every single expression? That is, and when I say expression, I mean this first piece right here, where it's multiplied, this second piece where all this is multiplied, and the denominator. They all have something in common. What do they have in common? Cosecant of 2x, and how many of them do they have in common? More. They actually have 4 of them in common, so let me show you. This one has a power of, I'm going to use green. This one has a power of 4, right? There's 4 of them in the first expression. There's 3 of them here and 1 more of them here. There's 4 of them there. And I have 8 of them on bottom, so that's at least 4 of them on bottom. Why does it matter? Well, if I have a term that's the same in all those places, I can just divide it out. They all reduce. So this piece and this piece along with this piece eliminate with the denominator to make that a power of 4. So I've got 2x here. And I'll just keep all the pieces the same otherwise so that I'm not going to confuse anything. And you got to admit, that was a pretty quick cleanup of a lot of stuff, wasn't it? It was a good thing to recognize at the beginning because it simplified a lot of things at one fell swoop. Now, there's still more that can be simplified in this second piece right here, right? I've got negative x squared times 4 times negative cotangent 2x times 2. What all can be simplified there? First of all, what's the sign going to be? There's a 2x at the beginning. What's the sign going to be? The sign, is it a positive or a negative? What goes after the 2x? Is it a negative? Did I see both the negatives? So it's actually a positive because those are being multiplied. I have 2 times 4, which gives me 8, and I have an x squared, and then I have the cotangent of 2x all over the cosecant, and I'll put it back in there just like they had it before, although you could certainly leave it otherwise. The cosecant to the 4th power of 2x, or you can read it right the other way. Nothing else reduces, right? There aren't any other pieces that simplify. There is one other thing that you might see the back of your book do. I'm not advocating it, but if you're wanting to check something, what you might see is you might see them factor that numerator and write this like this. They might factor the 2x out since both of those terms in the numerator have a 2x in them. It's not really helpful because it doesn't reduce anything, but you might see them do that. Okay, so either of these are fine. I would probably stop here if it were me working the problem, simply because that 2x doesn't actually help anything. But any questions on that? This was a difficult one. It had a lot of steps in it. A lot of your rules. Yes, Zach?
How did you get the top denominator to cancel with the cosecants? I thought you added the exponents, like if you have cosecant of 2x to the 4th, and then the cosecant of 2x to the 3rd, that would be...
Yes, you would if they were multiplied, but these aren't multiplied. There's a sign here that's subtracting them. So it's kind of like what I did in essence, and we did it once before. We did it a little bit differently, is we said, okay, look, this stuff at the beginning, which is separated by addition from the part at the end, they each have something in common. I could actually factor that out in front, kind of like I just did with the 2x.
Okay, so
I could factor that cosecant to the 4th out in front, and then I could cancel it with the denominator.
that makes sense.
Yeah. Any other questions on this one? All right. So Shannon seemed a little bit concerned about today because she said she didn't want to have to deal with some of the trig properties you guys remember doing. But I want you to recognize that if you recognize the trig properties, they're your friends. You should recognize a trig property here because if you do, this problem is very easy. If you don't, it's going to be a lot of work. Do you recognize a trig property here? Seeing a few nods. What do you see? What trig properties here? There's a sine squared plus a cosine squared property here, right? So let me first take out the 4 that we see in front of both of them. And then recognize I have sine squared of 3t and I have cosine squared of 3t. The angles match. If they didn't, we wouldn't even be able to be talking about this in this way. But because the angles match, that matches one of your trig properties. The sine squared of something plus the cosine squared of something equals 1. So this is 4 times 1. That's the original function. We haven't done any calculus yet at all. That was trig. What's the derivative? Big fat nothing, right? 0. If you don't recognize this, what it means is that you're going to have to do a chain rule to bring the 2 down, rewrite the sign to the new power. You're going to have to do the derivative of the sine, and then you're going to have to do the derivative of 3t. And you're going to have to do it all over again when you get to cosine. And then you're going to have a lot of simplification. And you know what's going to happen in the end? You're still going to get 0. All the work. So if you recognize a trig property that you can use it. Make it easier to work with, absolutely. All right, let's try another one. This problem asks us to find an equation of a tangent line. And we're given a function that is x squared cosine x. So as you're taking a look at that function, you have to be able to decide what rule do I need to use in this function. And you have to be able to decide this on all your functions now because they're going to all start intermingling, right? So obviously you've got a cosine rule. Obviously you've got a power rule. What else do you have in this problem? This is a product. Does everybody see it? You've got 2 pieces. Each of them have x in it, and they're multiplied together. That's a product rule. So we're going to have to use a product rule to do the problem, and in the middle of doing the product rule, we'll have the other pieces of those rules come into play. This one's not a difficult one to do the product rule for, though. So let's take a look at this one. By the way, just as a reminder real quick, why am I doing the derivative? Because that will give me my slope, right? When I evaluate it, it will give me my slope. Okay, good. All right, so what does the product rule say I'm going to do? Rewrite the first piece. That's x squared. What's my next thing to do? Derivative of cosine. What's the derivative of cosine, Nathan? Do you remember? Good, negative sine. Good remembering. All right, so that's negative sine. Am I done? Nope, I'm half done, right? What's next? A plus. Okay, that was almost a trick question, right? A plus is exactly what's next. And then what comes after my plus? The derivative of the x squared, which is 2x. And then cosine of x. Now, we can pull the negative out in front here. It's not a very exciting simplification step. There's really not a lot of simplification to do. And if there were a lot of simplification, I would be tempted to not do it anyway, because that's not what this problem is about. This problem is about finding what? The slope. I mean, at least this portion of it is about finding the slope at the value, in this case, pi halves, right? So really, I don't care what the derivative is. I really only care what the derivative is at pi halves. So that's actually what I'm looking for at this particular point in the problem, is to find what is this value when I evaluate it at pi halves. So if you have a unit circle handy either in your head or on paper, or if you want to have one handy as you're doing your homework, it probably will help you. You're evaluating each of these now inside of a cosine and a sine function. So you have to remember, what is the sine of pi halves and what is the cosine of pi halves? So let's start with sine of pi halves. Do you remember that one? That one's 1. Cosine of pi halves, that one's 0. Yeah, that one's 0. So this second piece right here, all of this ends up being 0 because it has a factor in there multiplying by 0. So my function's slope actually ends up being negative pi fourths over 4. Sorry, pi fourths, pi halves over 4. Get the right number in there. I know that looks like a funny value, but in order to do anything different, you'd have to approximate. We don't have any need to approximate. Your calculator will tolerate this value just fine. So we're going to leave it just exact with pi squared over 4. Okay? That's my slope. What else do I need? I need a y value. Right now I have my slope. That's what I just found. I have the x value. I've already boxed it in. This is x. I need my y value. And so how do I find the y value? Plug it in where? And what do I plug in? Good. I take the original function, like you said, and I take the original value given, and I plug it in. So we're saying f of pi halves, which is pi halves quantity squared, times the cosine of pi halves. And what happens? That's 0, because we already talked about the cosine of pi halves being 0. So this one is my y1 value. So now I have x1, y1, and m, and I can actually find the slope of my line. So the slope of my line would be y minus the y value equals my m, which is negative pi squared over 4, times x minus my x value, which is pi halves. And we'll do one little quick step of simplifying, and what do we get? Negative pi squared over 4x. And then what? Plus what? Yeah, we're going to distribute. So pi to the third, very good. Pi to the third over, careful, over what? 8. We're just multiplying, right? 4 times 2, pi squared times pi, so we get pi cubed over 8. Any questions on this one? All right, I think there's one more. Does that look like one more to you guys? All right, so this is an interesting problem. We haven't actually talked about out loud, I don't think, this notation right here. But you've encountered it and nobody's asked any questions about it yet. So I assume that you've seen it and or figured out what they meant. Do you know what that notation looks like or what that means? Okay. That notation is actually telling you it wants the 75th derivative. Brooks, you look like you thought that's probably what it was. You were trying to pretend like you didn't want it to be that way. You should have seen one in the homework. I think it had a power of 4. Did have to look, I was 4. So anytime you get more than a third derivative, they don't want to keep doing those little prime notations. You can obviously see why that would be problematic if you got too far in. So anytime you get more than doing a third derivative, they'll put a little exponent up there in parentheses, so you don't think it's an exponent. I mean, that's what it looks like, but it's not an exponent. It's just telling you what derivative is you want. I contend that you do not want to take 75 derivatives, correct? So that's not necessary to do on this problem, but we are going to take a few derivatives and see if we can identify the pattern of what's happening. Are you guys ready for that? So we're going to start with this original function, f of x equals the sine of 2x, and we're going to take a derivative. Now, Tyler, you're the one who brought it up before, so I'm going to ask you, what do you see happening here?
We'll have to take chain.
There will be a chain rule. Do you know what it's going to be? Can you tell me? What's the derivative of sine?
It's cosine 2x
Good.
times the derivative of the inside,
Which
is 0.
Close. What's the derivative of 2x?
Oh, 2x, it's
Not
2.
just the 2. The 2x is 2, yeah. Okay, and I'm going to write it in a little bit different order than what Tyler said. I'm going to actually put that 2 that was the derivative of the inside in front. Sort of like a cleanup step, but I'm going to write it at the beginning there. Okay, so we have 2 cosine 2x. Everybody good with that? That was a chain rule, because the 2x is inside of the sine. So the derivative of sine is cosine, right? So there's that cosine 2x, and the derivative of the 2x is the 2, so there's the 2, and I just wrote it in front instead of the back. Is that okay? We're going to do a second derivative. Okay, so I'm going to write this, and then I'm going to do a cleanup step real quick. This is a 2, because the 2 is a coefficient, right? And then what's the derivative of cosine? Negative sine. Actually, let me write it this way. Of the same angle, right? The angle doesn't change. But then I have to do what? The inside of the 2x. So I get another 2, don't I? Now I recognize that 2 times 2 is 4, but I'm going to write the negative here. I actually would like to keep it written as 2 times 2, and I'll show you why in a minute, but just bear with me and pretend like it makes sense even if it doesn't, okay? So I'm just going to leave it written right now as 2 times 2. Third derivative. That negative 2 times 2 stays because that's a coefficient. It's just the number negative 4.
How did you get it to be negative sine instead of cosine? Is that the chain rule?
No, it's the derivative of cosine. The derivative of cosine is negative sine.
Did you use the chain rule?
Not on that part of it. I mean, I'm using the chain rule on every part of the problem. That's where the 2 is coming from over here. But it's coming back from the very first screen, Grace.
I know it's that's
Right
what it is,
there.
but I'm just trying to see why you used it, because what part did you use the chain rule on?
I did it because I took a second derivative. I'm doing another derivative. I'm not simplifying. I'm continuing to take derivatives. So here's my first derivative. Stands alone by itself. To do a second derivative means I take that function and I do the process again. So I'm doing another derivative. So yes, there is going to be another chain rule because this 2x is still an inside function.
So I'm just trying to see where you used the chain rule, though.
I use the chain rule because the derivative of cosine is this
But
piece,
which part?
and the derivative of the
Rewrite
2x
the
is
same?
2. The 2x. The part that gets rewritten, and it always on this is going to be the 2x. It's never going to change. That's the inside function. That's the part that remains constant no matter what I change the sine or the cosine for it to being in the front. But every time I do it and I take the derivative of the 2x, it's the same, right? It's 2. It's 2. It's 2. So every time I do this, I'm going to get a 2 at the end over here, too. And then I just moved it to the beginning down here. So I've got the negative from the inside where this is part of the derivative of cosine. I've got the 2 from here, and I've got this 2 from over here. Okay, we're going to take another derivative. I'm going to take 4 of them. This is my third one. My third derivative, I've got the negative, the 2's and the 2's. That's the constant multiplier rule. And then I need the derivative of sine 2x. That's a chain rule, right? What's the derivative of sine? Cosine. Of the same angle, right? So still cosine of 2x. That angle still doesn't change. And then what's the derivative of 2x? 2. My next step, I'm just going to move that 2 in front with the other two 2's. So there's going to be 3 2's there now. So I have negative 2 times 2 times 2. There's 3 of them. Cosine of 2x. All right, so here's that notation with the 4 that we see come about. I want my derivative of the last function that I just found, right? The negative 2 times 2 times 2 cosine 2x. The piece at the beginning, which is equivalent to negative 8, just gets rewritten. It's a constant multiplier. What's the derivative of cosine? Negative sine of the same angle, right?
So when you rewrite the 2x, that's the same.
Yes, every time I rewrite the 2x, it's because I'm doing an inside rule that I'm keeping the inside the same. That's right. I need one more thing. What am I missing? A 2, because that's the derivative of the 2x. And I'm going to group that again at the beginning with all the other 2's. Oh, sorry, one more thing to notice. What else to notice here before I keep going?
Change sign.
It changes signs. I've got a negative at the beginning, and I have this negative right here, so this actually becomes positive again. So I've got 4 2's, and I've got a sine of the 2x. All right, so here's what I'd like for you to see. There's pieces of this. Let's talk about the 2's first, and that's the fun part. The first derivative, how many 2's does it have? The second derivative, how many 2's does it have? Third derivative. Fourth derivative. So how many 2's will a 75th derivative have? Okay, so is that part cool? Right, and that makes sense because every time you take a derivative, you get a 2 from the inside. So as I'm solving this problem up here in a moment, you know what, let's do this. I'm going to get 2 to the 75th. That is for sure going to happen. There are going to be 75 2's. Now I want you to look at what's happening with my sines. And that is like my sines and cosines. Here's sine. The derivative gave me cosine. And then the derivative gave me sine. And the derivative gave me cosine. And the derivative gave me sine. Right? They went back and forth all the way through there. So if you take a look at this real quick, notice, where do you get the ones that say sine? On the even ones, don't you? Right? The second derivative was sine, and the fourth derivative is sine. Every time it had an even derivative, we were actually getting sine. And every time it has an odd derivative, we're getting cosine. So since 75 is odd, this is going to be cosine. Of the same angle, it's the angle 2x that we had before. There's other piece that keeps changing. What other piece is changing? The positives and negatives at the beginning. I know we keep using the word sine and we mean two different things. But the positives and negatives at the beginning change, don't they? So this one it starts out positive. The second derivative is also positive. The third derivative is negative. And the second derivative is negative. The third derivative is negative, and this fourth derivative is positive, right? So we've got to figure out, is ours positive or is it negative? And you can't just look at even or odd, right? I mean, that doesn't work quite as cleanly as the sine or the cosine part of it. So there's a really quick way to do that, though. One quick way to do that is sort of noticing the fact that I went from sine to cosine to negative sine to negative I said that wrong. Started out with sine. I went to cosine. That was the first derivative. The second derivative was negative sine. The third derivative was negative cosine. And the fourth derivative was positive sine. This fourth derivative, sine, went back to the beginning, didn't it? It's a positive sign, just like I started with. Okay, so that means that if I wanted the fifth derivative, it would actually look like the first derivative. And if I wanted the sixth derivative, it would look like the second derivative. If I wanted the seventh derivative, it would look like the eighth derivative. I didn't say that right, third derivative. And if I wanted the eighth derivative, it would look like the fourth derivative. And then we would repeat. We could just keep going through this pattern and keep repeating as far as the sine and cosine and whether it's positive or negative. That process just keeps repeating and keeps repeating. So what we can actually do is we could actually look at what our exponent is. In this case, it's 75. And figure out if 4 goes into it. So 75 divided by 4 doesn't work out evenly. But what do I get if you put 75 into 4? What's the number your calculator gives you? Somebody grab it for me. 18, and 0.75 would be the same as 3/4, right, Zach? So this actually would mean 18 times I go through the list, all the way down to 4, and then all the way down to the power of the fourth one, and all the way down to the fourth one. I would do this, run through the list 18 times. And then if I wanted the 19th time through, right, after I did that, I wouldn't go through the list the whole way. I'd go 3/4 through my list. So I'd go through the first derivative, second derivative, third derivative. This number here on the top is equivalent to telling you that this is a third derivative. It's equivalent to the third derivative in terms of the sines and the cosines and the positives and negatives. So on the third derivative, I have a negative cosine. So on the 75th derivative, I also have a negative and a cosine. And we can do the same thing for the 100th one. So let's do the 100th one. So if I want to do, sorry, not 100th, 150th is what your problem says. 150th one, I want to go through the list 150 times. Well, first of all, let's talk about the powers of 2. How many powers of 2 am I going to get? Yeah, 150. It's a lot of them. It's a big number. And if I go through the list, and I could also talk about, this is an even, right? So is it sine or is it cosine? It's sine. And then I can talk about, is it positive or negative? Well, the positive or negative I can actually do by taking the 150, just like before, and dividing it by 4. What do you get if you tried to divide 150 by 4? 37.5. And I'm going to write it a little bit differently. I'm going to actually write that 1/2 as 2/4. Because then it's in the pattern that I can see a 2 over the 4 of them, and this 2 tells me I'm the equivalent to being the second derivative. And the second derivative is the sign positive or negative. It's negative. So on your 150th derivative, it's also negative. Now that's kind of interesting, right? It's a pattern thing, and it doesn't happen everywhere. It only happens with sines and cosines. And only sines and cosines that have a constant multiplier inside with that x. All right.